So in this lecture, this is lecture number 1 of a class in electricity and magnetism. And so the way I'm going to start it is by talking about electric charge. The learning objectives for this particular lecture are described here. Describe how an object may have what's known as a net charge. So net charge is an important concept that I'll go over. After some preamble, I'll describe here. There are some units that you should begin to sort of see through changing units between units of E and units of capital C, which is also known as the coulomb. I'll describe below. Explain whether a described process obeys these two different fundamental laws about charge, which I'll describe below. One is called the law of conservation of charge, very interesting law. And also another one, interesting for a completely different reason, probably, is the law of the quantization of charge. And then the last learning objective, predict how interaction forces may change in strength and or direction given a set of circumstances about electric charge. So in order to get you to learn to be able to do these things, I'm going to describe some stuff to you about electric charge. I'll start by describing exactly what about matter has electric charge and what is this feature of matter. So I'll describe that. I'll describe that electric charge is a measurable quantity. That is, experimenters, engineers, and physicists, they should expect that they ought to be able to measure it somehow, just like measuring mass or time or length. And I'll describe some units and some facts about protons, electrons, and neutrons. And then we'll talk about in what sense can things have electric charge, and this is where I introduce you to this buzz concept called the net charge. I'll give you an equation for calculating the net charge of an object or a system of objects even. I'm going to address the fact that the number of protons and the number of electrons in any sort of piece of material that we run across in everyday normal life is a stupid large number, really big. And then I'll go on to describe the conservation of charge. Above here, actually, I'm noticing that I didn't have a separate here is where I actually address one of those two fundamental laws about electric charge. This is the quantization law of electric charge. Actually, I should expand. I wonder if this will happen. Nope. So the quantization of electric charge. I'll sort of describe it here. This is the net charge calculation. This is the conservation of charge. I have an interesting example of beta decay. And then I'll describe some basics about how to know about electric force and what you can say if there are changes in the circumstances of having electric charge. I'll describe what I mean by that. Electric charge is an intrinsic quality of, I guess, the fundamental particles. You might say that another intrinsic quality that you already know about is mass. So an object has the mass it does, and this is something that is intrinsic to the object, also known as inertia in this case, right? And charge is another of these intrinsic qualities. There are a few other intrinsic qualities of fundamental particles, but you would learn about those in later classes. Yeah, so matter is made out of atoms, right? No surprise there. And atoms are little systems of a nucleus that is the protons and the neutrons, right? These are examples of fundamental particles that I described earlier. And then there are electrons as well. And so I like to use the symbols P plus for proton, N0 for neutron, and E minus for electrons. Yeah, and so we're already alluding to the fact, and I'm sure you already know this, but the proton is considered the positive type of electric charge. The electron is considered the negative type of electric charge. And the neutron is neutral. So we give it the charge 0, and hence the little 0 at the top. But yeah, so it's an so this idea of electric charge, it's an intrinsic quality of these kinds of particles. Yeah, just like these kinds of particles also have little amounts of mass. You'll probably remember, you can look it up yourself, the electron is a very low mass object. The proton and the neutron each have about the same mass. They're not exactly the same, but they're very similar amounts of mass, and they are each about 2,000 times as massive as the electron. All right, so matter is made out of atoms. Atoms are made out of electrically charged objects, so matter, the reason why we can say that matter can have electric charge is simply because matter is a system of objects that intrinsically have electric charge. Here's an interesting image for an atom. I really like the this is something that I saw a long time ago. So you imagine having some honey stuck in a jar, and the honey stuck in the jar is kind of like a nucleus where the protons and the neutrons live down in here. And then the electrons are a little swarm of bees that swarm around, and sometimes are sort of close to the nucleus, and sometimes they're pretty far away from the nucleus. And because, so these bees, they surround, and you can kind of see that I've drawn six bees, right? It might be this honey might be sort of 6 protons worth of honey, or some kind of image like that. But anyways, this right here is the atom. So let me remove the count of the bees. But the bees kind of swarm around this central nucleus of honey. So this might be a nice thing for you to keep in mind. All right, so let me move on and talk about units for electric charge. So I really enjoy this kind of a chart when I talk about units. So I'm going to talk about units second, and I'm going to talk about what's known as, or I call them, dimensions. These are physical dimensions, and these are qualities about nature that are measurable. So I'm not talking about when I say the universe is three-dimensional, I'm not talking about space dimensions. I'm talking about measurable qualities. And the units are what you measure against. So physical dimensions, length, sometimes used as capital L. So with lengths, we can use the SI unit of the meter to measure lengths, to measure time durations, which I'll give the symbol capital T. The SI unit is the second. That's what we measure. So we all have a basic idea of what the second is, and we can measure the quality of time duration against the unit of the second. So I could measure 25 seconds or 4 nanoseconds, etc. The last one that you already know about, or that's part of a prerequisite, is the idea of mass, which is one of the intrinsic qualities, as well as you might claim that there is a size intrinsic to certain particles as well. But anyway, so the SI unit is the kilogram. And then moving on, we get to add a fourth dimension. Forgive me for the reference to the space. But there is a fourth dimension of measurement called charge. And I'll designate that with a capital Q for the dimension name. And the SI unit is going to be the coulomb. So so this is the SI unit of charge, just like the kilogram is the SI unit of mass. So really quick extra note, composite dimensions, for example, volume is length cubed, and we can get the meter cubed as an example of a volume unit. Speed is length per time, for example, and we could use the SI units meters per second. And it turns out that there is an interesting dimension that involves the charge. This is called the electric current. And the electric current is simply charge per time. And charge, so this is the dimension, charge per time. So the SI unit will be the coulomb per second. And it turns out that the coulomb per second is also known as the amp. This is a unit of current. It's the SI unit of current. It's built out of SI units for charge and time. That's the basic idea. We'll see a reason to introduce the current later, but you know enough to not be surprised by this, I bet. So let me move on. Actually, I wanted to say, I'll say it on the next page. So the coulomb, there is another useful unit of charge, and it's just given the symbol lowercase e. We'll say that the charge of a proton, so I'm going to use the lowercase q sub p, this is the charge of the proton, it's equal to +1 times e, or just e. So this right here, this unit is the charge of a proton. And the charge of an electron, I'll show you, I'm going to say something interesting now. It's equal to -1 times this basic unit of charge called E. And it's also written as just simply -e. So the charge of an electron. And the charge of a neutron, remember, is neutral. It is 0 times the fundamental unit of charge called E. And it's just 0 times any units is simply 0. So these are the charges of these particles. I think it's interesting to note that the charge of proton is same amount as charge of electron. And as far as physics people can know and measure, they think it's exactly the same. So the quantization idea is one can never measure fractions of E. That is, you're only going to get integer numbers of lowercase e, sometimes negative, sometimes positive, or sometimes just none of them. And the idea is you can't measure any fractions. So I'm going to put in parentheses something about you. Some of you may be looking at physics and physics that's sort of extreme condition physics. And there are particles known as quarks, and you might go and look at that. You could check it out on Wikipedia, for example. But this is the quantization idea. There is a units conversion factor, and it looks like this. So conversion factors are always equal to 1. So 1 is equal to, so let me make it look very much like a 1. So it's 1.602 times 10 to the minus 19 coulombs is the same amount of charge as 1 E. And you can flip this over, right? Because 1 over 1 is also still 1. So 1 E divided by 1.602 times 10 to the minus 19 coulombs. This is a conversion factor between the units of the coulomb and the units of E, the fundamental charge, which is the quantized charge. It's the thing that you can never see fractions of. Right, so next topic in this very first lecture is how do things, and I'm talking about macroscopic now, but they could also be, or small, right? So how do things have charge? And the concept that I need to introduce you to is net charge. So the net charge of an object I'm going to call, say, Q net, or sometimes just lowercase q net. It doesn't really matter. You'll see both of these symbols in your homework, and you'll see me use both of those symbols. But the idea of the net charge is it's equal to. So you pick your thing and you count up, or your object whose charge you want to talk about, and you count up what is the number of protons, subtract off the number of electrons, and then multiply by the fundamental charge of the protons and the electrons. Yeah, so macroscopic objects are made, or are constituted from, or are based upon, or however you want to say it. So objects are made of a huge number of atoms. And there is a special number called the mole that I'm going to introduce you to. So here's the idea. So let me tell you about carbon. So carbon has, so one carbon atom is equal to a nucleus that has 6 protons. Most often it's also got 6 neutrons, although interestingly you can also have carbons with, I guess it's 8, yeah, 8 neutrons. Wow. But the typical carbon atom, that if you just pull it out of the ground, it's going to have 6 neutrons, 6 protons. And then if the carbon atom is neutral, then that means that the number of protons and the number of electrons are the same, and the neutral object has Q net equal to 0. So neutral means that the net charge of the thing you're talking about is equal to 0, and the only way that that can be true, because E is not 0, it's if the number of protons and the number of electrons match each other, and they precisely cancel. So a carbon atom that is neutral, that is, it has a net charge equal to 0, has a nucleus of 6 protons, 6 neutrons, and then it has 6 electrons in what is often referred to as the electron cloud. So this is the cloud of little bees around the honey pot. So if I add up the net charge, Q net in this case equals, so the number of protons is 6, the number of electrons is 6, and then when I multiply by E, I get 0. So that's a neutral carbon atom. A macroscopic sample. So let's say I've got a diamond, so I'm trying to draw a diamond here. Looks something like, I don't know what it looks like, but this is a diamond. And let's say I've got a, so this diamond is equal to an assemblage or system of 6.02 times 10 to the 23rd carbon atoms, right? So in this case, this diamond would have a mass of 12 grams, or 0.012 kilograms, this piece of diamond. But can you see that the number of protons in this 12-gram sample is, if I have this many atoms, and per atoms I have 6. 6 times 6 is like 36. So the number of protons is going to be some number that's crazy. It's going to be 3.6 times 10 to the 24th, right? That's an absurd number, huge number of particles in this 12-gram diamond. The number of electrons is going to be the same number, right? And can you see that adding or subtracting 1 electron from this big pile of electrons, it's hard to tell. 1 electron is hard to tell. Lose 1,000, it's also hard to tell. It's 21 places in if you lose 1,000 electrons. So when we talk about macroscopic objects and losing or gaining 1 electron, it's hard to tell, quite honestly. And within the significant figures, you may calculate that the net charge, even after losing 1,000 electrons, according to significant figures rules, you may notice that the net charge is still just plain old 0. Okay, so let me move on. I just introduced you to the idea of a net charge. I gave you an example of thinking about the number of protons, for example, in a 12-gram sample of diamond. Let me show you a units conversion real quick as an example. So if the number of protons equals 3.6 times 10 to the 24, right? So this is purely a number. Notice there are no units here, right? The total charge of 3.6 times 10 to the 24 protons, though, is equal to 3.6 times 10 to the 24 E, right? So notice that up here, this is an integer. It's just I have to go and count how many protons do I have. This is how many protons are in that 12-gram diamond sample. The total charge of that many protons, though, is this quantity. This is the charge of the protons in that piece of diamond. That's the charge of it. I'd like to convert this particular charge, convert to coulombs instead. So whenever you do units conversion, remember, right, the goal is to not change the value. Right? In converting units, I don't want to change the amount I'm talking about. I just want to change the units that I'm describing the amount in. Right? So I don't want to change the value. Is to not change the value. And the way that you don't change value is you multiply by 1. Right? Whenever you multiply by 1, you don't change the value. So here is my value. 3.6 times 10 to the 24th E, right? This is my value. And it is equal to, I don't want to change the value, so I need to keep it equal. It's equal to 3.6 times 10 to the 24th E times 1. So I can multiply by 1, and I have not changed the value, so the equal sign is still true. Equal to 3.6 times 10 to the 24th. And now let me remind you of our conversion factor. Conversion factor is, here is some convenient forms of 1 for converting units between electron charge, or proton charge and coulomb. So I would like to multiply by 1 in the form that gets rid of E and replaces it with C on top, which is this form. 1.602 times 10 to the minus 19 coulomb divided by 1E. And you can see that the E's will cancel when I multiply by this version of 1, and out pops some craziness. 3.6 times 1.6. I'm going to play a game. I'm going to say this is kind of like 4, and this is kind of like 1, so I'll go up with this one and down with that one, so it's basically like about 4. And then 24 minus 19, so it's something similar to 4 times 10 to the 24 minus 19 coulombs, so which is equal to 4 times 10. So 24 minus 19, I think, is 5 coulombs. So it's about, wow, that's huge, actually, 400,000 coulombs, right? So there's 5 zeros, there's the 10 to the 5th, 400,000 coulombs. Luckily, we also have 400,000 coulombs, negative 400,000 coulombs of electrons charge, right? Yes, so the net charge is this plus that, adds up to 0. Okay, next topic is the law of conservation of charge. The idea here is it really refers to the entire universe. So if I take all the particles, all the particles in the universe, there is, and it's absurd to imagine actually trying to do this, but the idea is there is a certain net charge of the universe, right? So it's the net charge of the entire universe, the number of protons in the universe, minus the number of electrons in the universe times the fundamental quantized charge E, right? So this is talking the entire universe. And the law of conservation of charge simply says that the net charge of the universe cannot change in time, right? And the other way to say this, right, that is that the net charge of the universe does not change, no matter what happens in the universe, or no matter, what of all the possible physical things that could happen in the universe, this is strictly just true. The idea is, it's a really important one. There are no processes in nature that result in a change to the net charge of the universe. It's a pretty crazy statement, but the point is anytime anybody pays attention to something physically happening, the total charge of the system, all of the parts involved, the total charge simply doesn't change. That doesn't mean, though, that the number of protons or the number of electrons doesn't change. In fact, actually, there is a process referred to as beta decay, and beta decay looks like this. At some earlier time, what the universe has in it is a neutron, and it's all by itself. A little bit later in time, when you check on this neutron, you find that you cannot find it. The neutron is gone, and in its place are a list of 3 particles: the proton, the electron, and something called the anti-electron neutrino. I'll put it in quotes, but the symbol for the anti-electron neutrino looks like this. This is the Greek letter. How do you spell this? Maybe it's just Nu. Anyways, it's Nu is the name of the letter, and it's an antiparticle, strange thing, and it's of the electron type. And so the net charge of the objects involved starts off as 0 at some earlier time. At some later time, you don't have the neutron. The neutron is gone, and in its place is a proton plus an electron plus an electron, anti-electron neutrino, has no charge. It's a neutral particle. Neutrino refers to the charge. And net charge 0 before, and later net charge is still 0. We don't have a neutron anymore, though. And previously, we didn't have that proton. We didn't have this electron. And we also didn't have this weird neutrino particle. So even though the particle counts might change, the net charge does not change. This is the idea. So the last thing that I'm going to describe is electric force. And I want to remind you, it's, sorry, electric force basics, and what I mean by this is it's a qualitative intro to how the forces work. So let's say that I'm going to be a little bit diagrammatic. This is a small positive charge. We could say that what I mean by this is the number of coulombs is a small amount of coulombs of charge, and it is positive. Here's an example of a diagrammatic large amount of negative charge. So this is large negative charge. All right, and then the other diagrammatic thing I'm going to remind you of is forces are vectors. That is, they have a strength that's also known as magnitude, right? And SI units, I'll remind you, for example, newtons as the unit of force strength. So forces are vectors though, so that means that direction is also an important issue. So I'd like to tell you about basic electric force, and I'm going to comment on direction first. The direction rules or basics to electric force is opposite charges attract and like charges repel. That's all you got to know. Attraction and repulsion are one-dimensional issues. That is, I don't need to know that I am in 3D or 4D or 5D or even 2D, and one dimension is enough. So let me show you. So for directions, let's imagine opposite charges. So let's take these two charges that I drew up here. So if I put the plus charge here, it's pretty small, and I put the minus charge here, what's going to happen is they're going to attract. So the positive charge feels a force towards the minus charge, and the minus charge feels a force towards the positive charge. That's what's meant by attraction. You could say that this force right here, the one that I drew first, this is the force on the positive charge by the negative charge, and this force right here is the force on the negative charge by the positive charge. Can you see that the plus and minus are swapped and the on and by? And what I'm alluding to is Newton's third law. So the attraction of the plus towards the minus is going to have the same strength as the attraction of the minus towards the plus, even though they are different amounts of charge. So this is a big deal. Like charges repel. So let me make a plus and a plus. So now they seem very similar, but let's call this plus charge A, and this is plus charge B. Plus charge B is repelled from plus charge A, and plus charge A is repelled from plus charge B. This is the force on A by B, and this is the force on B by A. And Newton's third law is they are opposite in direction, but equal in strength. These are opposite in direction and equal to strength from each other. These are Newton's third law pair forces that I'm describing. These are vectors as well, right? So let me say that the force on B by A is equal to the opposite of the force vector on A by B. And interestingly, I get the Newton's third law direction issue just from or actually not the Newton's third law, just the force direction is told to me in this kind of like code. This is the code for directions. For strength, we can calculate, that is quantify, with what's called Coulomb's law. And this will come later. I'll describe Coulomb's quantification or formula or equation later. But the strength is simple. If there is more charge involved, the strength increases. That is, if I use large amounts of charge, then all the force arrows will be bigger, they're just stronger. And if I use small amounts of charge instead, then the force arrows will all be smaller. So there is something about strength and amount of charge. And another one is if the charges involved are further apart, the strengths of the forces decrease. That is, if I imagine charges A and B being further apart, I should expect the force arrows to shrink. Their directions won't change, but their sizes will diminish. So there's a separation issue when judging the strengths of forces involved in electric force interaction. All right, that's the lecture.